So let's look for a few solutions of the Friedman equation. Let's first start with an empty universe. So for an empty universe, I mean a universe without matter, you simply set the density equal to 0, get rid of the second term on the left-hand side, and the equation simply becomes h squared a squared is equal to minus kc squared. Now, because h is equal to 1 over a dA dt, this becomes simply dA dt squared is equal to minus kc squared. Now, because I have squares on both sides and a negative sign, then k for this universe must be negative. So let's work with the modulus of k and rewrite this then in terms of the modulus of k. dA dt is equal to the square root of the modulus of k times c. So this is readily integrated to yield the scale factor of an empty universe as a function of time. Now we need to find the value of k. So what is the value of k? For that, you need to go back to how we defined k, which was as a function of the energy. Now invert this to find k in terms of the other quantities. K is equal to minus twice the energy over m omega squared c squared. Now the energy is constant, omega is constant, the mass is constant, and the speed of light is constant. So k does not change with time. If we find k for one particular time, we find k for all times. So let's go back to the Friedman equation and apply it to the present time when the scale factor is equal to 1. If the scale factor is equal to 1, that means that we are using now the Hubble constant as measured today. Let's call it h naught, and you find the value of k for the empty universe. So that means that the square root of the modulus of k is h naught over c. The scale factor of the empty universe then is simply h naught times the time. The evolution of this empty universe is shown here in this figure. The present time has scale factor 1, so the time is equal to the inverse of the Hubble constant. We can define here Th as the inverse of the Hubble constant. That means that the Hubble constant gives you the age of this empty universe. So we can define the Hubble time, Th, as the inverse of the Hubble constant. And then if we measure the Hubble constant by Hubble law, then I have an estimate of the age of the universe. The grid values of the Hubble constant are shown here. They hover around 70 kilometers per second per megaparsec. If you convert that to inverse second, that gives you about 2 times 10 to the minus 18 over second. So you invert that, you have an age for the universe, which is about 0.5 times 10 to the 18 seconds. That is roughly 14 billion years. So if the universe was empty, this would be its age.